Okay. Has that worked? It says stream health is excellent. And I see myself. And if I unmute, I'll hear an echo. And if I unmute, I'll hear an echo. Yeah, wonderful. Okay, so that seems to be working. The other thing that I maybe want to do is record this. The other thing is to actually put the link in in Zulip so people can see it. How do I actually get the link? This is so frustrating. YouTube doesn't actually. Stream URL. But that is obviously not my stream URL because it doesn't have anything to do with my an identifier for me. Like if I go to YouTube, can I see my own face? View my channel. Yeah, this. Great. Copy link address. And if, for example, I go over to here, paste it in, I assume my face will appear. Well, my face has appeared, but I have not actually. I assume my face will appear. Okay, there we go. So I guess it's successful. Wonderful. Okay, so that seems to be working. Okay, but I should have copied the link. And there's some way of, there's like some Zulip thread. Stream, live stream. In live streams. Live stream announcement. Okay. I decided to do a bit of live streaming today. At this link. It would be wonderful if macOS didn't cover up what I'm trying to write on, but that's great. Okay, so that's there now. And I should also start the recording. Okay, start recording now. Okay, recording should now be started. And maybe I can now discuss my my vague plan for what I'm doing. Okay, so what am I doing? Yes, okay. So does big, yeah, so this, what is this? This is a, well, apparently I asked this question back in 2020, right? So I don't know if this, if every computer science student has this experience, but it was definitely told to me several times that big O is not a total order. And I guess I can click on this link and it'll explain why. But the point is that sometimes people ask, oh, is it always true for any pair of functions that one of those functions is the big O of the other function? And the answer is no, because you can have these sort of wildly oscillating functions that depend on whether the input is even or odd. And so that's all well and good, but it's not very satisfying, because if you are used to doing things in I guess computer science or math or whatever, you always see that the functions that you're told are the like the asymptotic behavior of like like common operations that you do. They always have a very particular form, and basically they're always expressed using like logarithms and exponents and addition and multiplication and maybe some roots as well, and all of these things. And so it's very sort of frustrating that like okay the right in the answer they give, it's just like this weird wildly oscillating function, and you want to know the answer. Okay, but if I give just like very well behaved functions, is it always going to be the case for functions like that? And so apparently the answer is yes. This was shown by Hardy in his monograph Orders of Infinity. And so like when I was like, yeah, when was this message? This message was sent in like 2020. And so I clicked on this link and I was like directed to this PDF. And it's like 100 like page PDF of a tract, a tract which was probably written in like release date 2011. Okay, well I don't actually think that must be the like Gutenberg release date, because this was written long before 2011. All rights reserved by G.H. Hardy. Yeah, 1910. So like over 100 years ago this was written. And so this is like a sort of like textbook about things. And okay, so I think the key like chapter that we're interested in is this like chapter 22, which is this logarithmico-exponential scales, and this is where he like answers this question. And so we've already seen like various functions are asymptotically greater than the other functions. And so this basically this chapter is all about like, okay, we have logarithm, we have exponents, and we want to start like proving, okay, certain ones of those are asymptotically larger than the others, and I think this is the key theorem here. So like a logarithmical exponential function is what he calls it, and then he switches to calling it an L function. Any L function is ultimately continuous, of constant sign, and monotonic. And as you go to infinity, it either tends to infinity or to zero or to some other limit, right? So it doesn't oscillate, or at least it doesn't, I guess you could say at least it doesn't like oscillate like wildly. I'm not exactly sure. It might not be a very important distinction. So basically the thought is like, okay, I was very very interested in this theorem, but like this I've like previously I've tried to read this a few times before, sort of lightly, like trying to figure out what is going on here, because it's like written in a sort of confusing way. And he uses like terms like algebraical function, and it's like I don't know exactly what that means. It's like it has something to do with the things that are described up here, but it's sort of like not very easy for a like to sort of grok it in terms of how I would formalize it in Lean. But I also saw that there was at least one other person who had made some pull request. Let's see, what was it? Yeah, okay, so there's like this pull request here to the formal conjectures. Here, I can copy it over, right? The formal conjectures library, which is this pull request, which has this like the common elementary growth functions. I guess elementary seems like a more sensible term to me, really, than logarithmico-exponential, because I basically understand what's going on here. But yeah, so the point is, yeah, we have exponents, logarithms, multiplication, addition, and the point is we want to like prove that they're well behaved. And so I was reading this over recently, and I sort of thought, okay, I feel like I understand this better, and maybe I should try and formalize it, or at least try and state things in a way where it would be like possible to understand what's going on, so that when I want to convince myself that this theorem is true, I don't have to read through the sort of like semi-archaic language here, and I can just like refer back to like a Lean proof, ideally. Yeah, so we have like degree and order. There's various things. So I'm going to try and go through and maybe like prove. I don't know if I necessarily want to do a complete proof of this theorem in Lean, but maybe if I can at least formalize formalize the theorem statement, or formalize maybe a version of the theorem statement which handles the things that I want to handle and maybe like makes clear exactly what's being stated. That would be like a good procedure to do. And so that's what I thought I would do today. Okay, so now I guess I will try and begin that. Okay, I have a question. Why didn't you previously try to prove a lemma from AKS? What about the effort in 34507? Oh, I don't know about this. 34507. Yeah, so I guess the answer is yes, I did do something formalizing a lemma from AKS. I think so. I did end up like formalizing that. I ended up putting it in one of Numena's repositories, just because it seemed like a convenient thing to do. Yeah, so I don't know what the status of this proof is at this point, because I think the thing about the AKS proof is that like even if you could successfully get, I guess this is getting into my personal feelings on like primality testing in proof assistance, but even if you could get the AKS, even if you could prove what you might call like the AKS theorem, even if you could prove that AKS was a correct primality test, right? That the algorithm AKS always correctly determines whether a number is prime or not, there would still be a long way to go to actually get like a useful thing, because on one level the AKS test is it's a polynomial time complexity, but it's like not a very good polynomial time complexity. It's like n to the 5 or n to the 6. And so it seems like there's probably a lot of sort of more difficult things that go into this proof besides just the one part that I was proving things about. But yeah, so I think that lemma went into like a repository of Numena's, and probably this one will as well. But they'll probably be released at some point in the next few months or so. Okay. Yeah, so to continue with what I was doing, define a logarithmico-exponential function shortly after an L function. Okay, so I guess the thing that I was going to do is like, okay, we have a definition. So for example, in this one, there's this functions of elementary growth, and you can just define like a inductive type, right? Inductive elementary growth, which has like a bunch of ways of defining a function. And I guess there's like a few ways of doing things here. I guess I'm probably just going to define things myself. So what if I go to, where would be a good place? I guess it doesn't matter. I'm probably going to move this anyway, but so if I go to, for example, it doesn't necessarily matter where I put this, but if I like make a file here, which is about like logarithmico-exponential .lean, and I can say something like, I want to make an inductive type. Okay, well, I probably have to like copy a bunch of boilerplate so that I successfully am able to like have a working lean file, something like this. So I want to be able to define an inductive type that would go something like, okay, no, this is not the inductive type I want to define. Logarithmico-exponential. Wonderful. Yes. And so what are the things that I want? Okay, I think I want this to be a real number because probably the thing deals with real numbers. I want an ID. Yeah, what is a logarithmico-exponential, right? The point is basically there's many ways of constructing a quote-unquote logarithmico-exponential function. One thing I can do is provide just, I guess it's more appropriate to call it x here, and just say, okay, I have the constant function x. Another thing I can do is the identity function, and that is just the function that takes in x and returns x. So that is another, maybe like C would be better, in fact. Okay, so that's great. Yeah, like the point is that these are more appropriately termed like f and g rather than whatever they currently are. FG, FG, log exp add mul. Yeah, and so okay, so let me see if I'm thinking about this right. The point is, for any logarithmico-exponential function, we can also consider the logarithmico-exponential function, which is obtained by applying log to the output of that function. And similarly, we can do that with exp, and similarly, we can do it with add and mul. And we could also do like pow. We could do it, in fact, pow with f and g, right? And we could also do like roots. But this starts to get into like, so if I return to the paper, right, or the book or whatever it is, so he defines, how does he define? It's like a logarithmic exponential function is defined as a one-valued function defined for all values of x greater than some definite value. Okay, well, we're going to sort of get into complications with x being greater than some definite value by a finite combination of the ordinary algebraical symbols, such as plus, minus, times, divided by, and square root, or nth root, as well as the functional symbols log and exp, operating on the variable x and on real constants. Okay, but there's some complications here, and there's some like interesting notes here, right? Which is one of the notes is that like this is maybe like too elaborate a definition, because if I consider, I guess this is true of pow as well. So I could define nth root as a form of pow, right? The nth root of something is just that thing raised to the power of 1 over n, right? So I could if I wanted to say something like root here, I could do that, right? I could say I have a function f and then some natural number n, but really another way that I could just write this would be to write root in terms of pow by providing f and then saying g is just the constant function, which is 1 over n. And similarly, right, I have add and mul, and it says that I also need, subtraction and division. But I don't really need subtraction and division, because like for one thing, I have the constant -1, right? I can always create the constant -1. So I can just define subtraction as I add, like I take f and g and I add f to -1 times g, right? That would be equivalent to subtraction. And similarly, I think you can do division, right? Well, I mean, so like the additional factors, because we have log and exp, we actually don't need addition at all, right? Or we only need maybe one of addition and multiplication, because the like trick we can do is we can say that addition is defined as log of exp of a times exp of b, right? If I have exp of a times exp of b, that's just exp of a times b, or sorry, it's exp of a plus b. And if I take log of that, then I just get x plus b. And I think that works even if you have, yeah, I mean, that works even if you have like negative numbers. If you go the other way, you can maybe try and define multiplication in terms of log, but you would run into some like trickiness with, you would probably run into some kind of trickiness with negative numbers, because if I wanted to define multiplication using addition logarithm and exponent, what I would do is I would say log of x, or log of x plus log of y, and then I would take the exponent of that. But then that leaves the question of what happens when one of those is a negative number, or 0 for that matter, and that would be more complicated. So, I mean, so when I was reading this a few days ago, I feel like I came to the conclusion that I maybe did want to have, yeah, and I mean, another consideration is what happens in the rest of the proof and like which of these concepts are used in the rest of the proof. So I think the idea that I came to is that I probably don't want, I don't necessarily want POW, because I can define that in terms of, like, I can define f to the power g as the exponent of like of f times log g or something like that. Yeah, of g log f, you know, in whichever order. And so I probably don't want this, and I probably don't want root, but I maybe do want the other things, even if they are redundant. Like, for example, I want, like, maybe what I want is like neg to like take the opposite of something, and maybe inv. But I don't necessarily want POW as a separate thing, except that maybe I do want to like take like natural number powers of things, but that's maybe not so important either. So I can just I think I'll stick with this as the set of things that I'm going to allow myself to do, and we'll see if I have any like additional like issues later. Yeah, okay, so I have this. Okay, so end computability. I don't know why end computability is here. I do have an end public section. Imports are out of date. Okay, well, clearly I should get the cache, and then did I already get the cache? Seems like I already got the cache. Okay, great. So okay, I'll just get the cache again to make sure that I have the cache. And then I will, the next thing that has to be done is command shift this. So now I'm here, and maybe what I want to do is like restart the server just to make sure that I'm on the right, that my server is running the right lean version. Unknown identifier R. Okay, so clearly I should port public imports. Yeah, so it knows that I need real basics in order to do this. And public section. Yeah, I don't know what the issue is here. Okay, and so I have this inductive logarithmico-exponential. And the point is I should also be able to do like eval. Like, so I want to be able to define logarithmico-exponential.eval. Yeah, naturally. So what do I actually have here? Failed to compile definition because it's non-computable. Yeah, that's fine. It's probably going to remain non-computable. Unknown constant real.log. Public import. Yeah, so like where is log defined? Probably I'm going to get like a ton of stuff. It's in like real special functions or something. Like data, real. Okay, so clearly this is a job for the MathLib docs page. The thing I'm looking for is real log. It is in MathLib analysis special functions log basic. Okay, cool. I will and probably exp is the exact same except that I write exp here. I'm just going to assume that that's the failed to build mod. Okay, maybe not. Real exp is in MathLib analysis complex exponential. Okay, cool. So this is not a real file. I'll paste that there. Okay, and now it's saying it failed to compile definition because I have real numbers here, so I'm just going to say non-computable. Can I say like non-computable section? I don't want to necessarily deal with, is it theory? Yeah, okay, cool. So that works. And so this is the, yeah, so this is just going to be like the real inverse. All of these things are real numbers. A val is something that takes in a logarithmico-exponential and a real number input and gives an output. Okay. So let's see if I can actually, so this is, yeah, I think this is fine. Just to return to the book and make sure that I have something that really captures everything here. So the point is, a one-valued real function defined for all values of x greater than some definite value. Okay. Yeah, so the one thing that I'm worried about here is sort of like these. It is true that all of these are defined on all values greater than some value. I guess that's part of what we're trying to prove, right? Because the point is, if I have like logarithm or inverse, those functions are not defined at 0. And if I do sufficient number of additions, I can get an undefined point wherever I want. Of course, in lean, those things are just defined to be 0 at those points. And so really what I have here is a bunch of functions that are sort of approximating logarithm and inverse, but they're defined everywhere, and they have like special exceptional definitions at particular points. So I think it's ultimately fine, right? Because probably it doesn't affect the theorem, because probably there's ultimately only going to be like finitely many of these undefined points. And so I don't think we necessarily have to worry about it too much. But okay, so that's something to keep in mind, I guess. Finite combination of the ordinary algebraical symbols. So plus we have add, minus, I guess we can call that neg, right? Times, divided by, we have those. We have divided by in the form of like the inverse function. And nth roots, right? I'm claiming that I have nth roots because I can do this log exp trick, right? So like if I want to, here I can define logarithmico-exponential dot pow, right? It takes in f and g, which are logarithmico-exponential, and it carries out this operation, right? It says g times log f. If I take the exponent of that, what I really have is f to the power g. And so if I can get this, I can get, powers. And if I even want to like get roots, I could say something like def logarithmico. Yeah, okay, I guess I can get sub 2, right? I can also def get div by this, and then I can def get like root. Yeah, this is sort of interesting. It's wanting to find like absolute value as well, because it's saying that I can just take the exponent of the log of something. This is unfortunately not the absolute value though, because if I have 0, then the result of that is going to be log of 0, which is defined to be 0. And then the exponent of 0 is 1. So this function is not actually the absolute value function, because it takes the value 1 at the input 0. So that's not necessarily something I want. But what I do want to say is I can do like root. So I have that, and it's just pow f to the constant whatever n. Yeah, that's great. So I feel confident that I can do the things that I want to do here. Okay, so yes, all of these, I feel like I've captured the class of functions here. Maybe modulo some weird constraints around like being not the right value at certain points. Operating on the variable x and on real constants. Yeah. It is to be observed that the result of working out the value of the function by substituting x in the formula defining it is to be real at the stages. Okay, so this is some comment. Yeah, so as I recall, this comment is a comment about the thing that I was talking about, where it's like, okay, sometimes things will be undefined. And it is not very good that things might not be undefined. And I feel like Hardy's attitude is just like, okay, well, you should be careful to never define anything that would be undefined at any point. Um, Whereas the attitude that Lean takes is more along the lines of, okay, we will just define a junk value, and the theorem will still be true even if we have junk values, right? It is important to exclude such a function that is like cosine x, right? Um, right. And so the point here is that, like, okay, with a suitable interpretation of the roots, it's equal to cosine x, but that's not the interpretation of the roots that would be taken here, right? If I try to take the square root of something, what happens if I try to take the square root of a negative number, right? Well, I'm raising it to the power const 1 over 2, which is just taking the exponent of the multiplication of 1 over 2 times the logarithm of that thing. But if it's a negative number, right, I'm just taking the absolute value. So it's really the absolute value. Like, I think I think the square root function that would be naturally defined if you use this is going to be sort of like a comes down and goes up and over thing, right? It's going to be like reflected across the y-axis. So, I guess he has one way of like saying we exclude such functions, and we have our way of defining what those functions would be. But nevertheless, we have the following theorem, I think, and I think this like theorem should still hold true even with the junk values. Okay, any L function, right? But there's a lot of parts to this theorem, so I'm going to have to think about how it's best to formalize it, right? Because part of the proof is that some of these properties follow from others. So it's one of these like theorems where it's like actually like 3 theorems in one. Any L function is ultimately number one, ultimately continuous, right? So for sufficiently large, and it is continuous on. Okay, let me just like try and like state the theorem as written. Just like main theorem, logarithmico dot main theorem. Yeah. Okay, yeah, so I think, yeah, I'm going to, any L function. Okay, I'm just going to say there's one L function that I have. What does it want to write for me? It wants to write, for any L function, there exists a constant real greater than 0. Okay, let me just like try and start writing things. There exists, what I want to say is that there's a constant such that f is continuous, is ultimately continuous, which I take to mean it is continuous on a upwardly infinite interval. It is continuous on some upwardly infinite interval. So I think there is some c such that f dot eval. Okay, continuous on. Is there like a continuous on? I think that continuous on is the right. So topological space. It's just a prop that takes this and a set. Okay, great. So I'm saying that continuous f dot eval is continuous on the set dot interval closed infinite c. And if I wanted to, I could just like end the theorem here and say bye sorry. Right. So this is one statement that he's saying. And so, yeah, like trying to continue to break it up. Yeah, okay. Let me just try and like define a bunch of separate theorems. The The tricky part is that like I know it's going to be like an inductive proof that involves all three theorems at once, but let me just try and define the theorem separately. Any L function is ultimately continuous. Any L function is ultimately, I think, okay, of constant sign. Any function, L function, I think, is ultimately of constant sign is what he's trying to say. So he's trying to say that theorem ultimately constant sign there exists a C such that for all x greater than C, this is not a very meaningful statement though. If f of x is not 0, then it is positive or negative. Okay, well this is just tautologically true. The point is that for any f, there exists a sign. The point is that the sign of a function is either +1 if it's positive, 0 if it's 0, or -1. Okay. The point is that there's one of three possibilities. One is that there exists a C greater than 0 such that for all f dot of val x is equal to 0. That is one possibility. Or it's always greater than 0, or it's ultimately less than 0. Yeah, so I think this is ultimately constant sign. This is ultimately continuous. Let me just write ultimately continuous. Continuous. Okay. Ultimately continuous. And ultimately of constant sign. What else? It is also ultimately monotonic. And presumably I can say monotonic, ultimately monotonic, right? Monotonic. But the issue is that monotone in lean is means that it's going upwards. But what Hardy is trying to say is that it either ultimately goes always upwards or ultimately goes always downwards. So ultimately, like tonic is maybe a better word, because it's the point is that there exists a C such that it monotone on, or I think monotone includes, yeah, so you can be equal and still be monotone. But so that's one possibility. Or antitone on, great. Okay, so that is true, that is true, that is true. Further, if f and phi are L functions, one or another of the relations f is asymptotically greater than phi, f is asymptotically equivalent to phi, f is asymptotically less than phi, holds between them. Okay, I think I'm not going to prove this part of the theorem for the following reason. I'm pretty sure that the first part of the proof is basically just to reduce this part of the theorem to the earlier part of the theorem and then never mention the second part of the theorem again. So I'm pretty sure that I'm totally safe if I say, okay, these relations things like follows from the earlier part of the theorem without worrying about the consequences there. Right, we may classify, okay, I think that's basically what happens here, right? If I scroll up in this book somewhere, there's like a formal definition of these things, but it basically just means, I think, that if you divide one by the other, it's ultimately it's like ultimately like grows forever or something. And the point is basically the way that this is proved, right? Let us observe that if f and phi are L functions, so is f over phi. And the point is that these things are just defined in terms of the value of f over phi. Hence, the last part of the theorem is a mere corollary of the first part. Okay, so that's basically just what he's saying. So I think we just don't have to worry about this this part, and I'm not going to focus on it. I think it would be best to have a def that actually gets the constant C for all the properties together defined recursively. Yeah, then to avoid all the exists. Yeah, I think you're ultimately right. I think I'm ultimately going to have to like rewrite these theorems into one theorem because I think, the point is that we're going to do some kind of induction on the structure of the logarithmico-exponential function um, in order to sort of prove all three of these properties simultaneously, right? I'm going to like prove that the ultimately tonic things for a logarithmico-exponential function of a certain complexity is dependent on the like ultimately constant signness of like the derivative of that function. So we're about to get into it here, right? We may classify L functions as follows by a method due to Liouville. An L function is of order 0 if it is purely algebraical. Now, okay, purely algebraical. He uses the word algebraical, and for the longest time, it's like, okay, what does algebraical mean? I guess it means like with the ordinary algebraical symbols. So I guess what he is trying to say is that it's like, okay, we could have done this inductive definition, and we could have left out the log and exp, and we could have added the root symbol, and that would have been another class of functions, and that would be the class that is called algebraical functions. Now, I find it pretty inconvenient to work with the root, and so I was reading. Okay, we're gonna see if I'm dumb or not, but I was reading the proof, and I'm pretty sure you don't actually need to include the root in the definition of algebraical functions in order for the rest of the proof to work. So what I'm going to do is sort of live dangerously, and so what I'm going to assume is that an algebraical function is just defined as sort of like a rational function, right? It's a function defined using add, neg, mul, and inv. And that's basically going to be my strategy for doing it. So like I guess if I wanted to, I have logarithmico-exponential here. What I could maybe do if I wanted to would be to like write another inductive, right? Like inductive, like algebraical. And that would just like, so yeah, so it would be exactly these things, right? And the point is that log and exp aren't present. And if I really wanted to, so I could like organize it like this, just to be a little bit more friendly. And if I really, really wanted to, what I maybe could do is I could say something like, this would be tricky though, because you can take algebraical functions of logarithmico-exponential functions of like multiple. The issue with algebraical is that like, I think that I want to have a definition of algebraical that allows me to have higher arity, right? I want to have like multiple different like inputs and like define like multivariable polynomials basically, and multivariable rational functions. But so that's just my sort of vague recollection. Okay, so there's an important concept of complexity that he's about to define somewhere here, right? We may classify L functions as follows by a method due to Liouville. An L function is of order 0 if it is purely algebraical, of order 1 if the functional symbols which occur in it bear only on algebraical. So basically we have an inductive definition. Yeah, we just have an inductive definition, logarithmico-exponential, right? It's sorry, yeah, the order, right? Order is what we're defining. Logarithmico-exponential dot order. And the point is that it's the order is the number of nested log or exp. Log and exp expressions. Okay, no, not with this additional. They don't count in opposite directions. They both count for 1. So taking the logarithm of something makes it a higher order, and taking the exponent of something makes it a higher order. And if you're not doing either of those operations, just the max of the orders that you have. So yeah, so it actually wants to be this. Okay, so now it's given me something, and I need to check that it's right. So we're saying the constant is of order 0. Identity is order 0. Addition and multiplication take the max. Negation and inverse keep the order the same. And logarithm and exponent increase the order by 1. Okay, I think this is a correct definition for order. Yeah, thus x to the power x is equal to e to the log x, e to the x log x. And so this is order 3 because we have log. We have a logarithm here, we have an exponential here, and then we have an exponential here. And these two things are multiplied together so they don't like increase. Yeah. Okay. As the results stated in the theorem are true of algebraical functions, it is sufficient to prove that if true of L functions of order n minus 1, they are true of L functions of order n. Okay, right, yeah. So, right, the results, right. Basically, the point is, this is true, the results of the theorem, right? Okay, so like we're here in the results of the theorem. And so like, yeah, to basically take Add Assembly Wizard's suggestion, what we can do is like combine these theorems into a main theorem. Main theorem. And it's going to include all of these. Okay, so I basically want to surround that in parentheses, and I want to delete all of this. And I want to say something like, this is true, and right, I'm going to like surround the 3 parts in parentheses, right? So I'm going to surround this in parentheses too. And I'm going to say that this is true, and this is true. And so this is now a main theorem that encapsulates all 3 of these parts. And like rather than all of these, right? So I can say this in a more better way. I can just say exists a c greater than 0, comma, such that all of these things are simultaneously true. And I don't need any of these ones here because I can just have it be true for everything. So there exists a c greater than 0 such that f is continuous and strictly positive / strictly negative / 0, and also it's monotone and it's also antitone. So I think that all 3 of these things are handled. Okay, so that's the main theorem. And so the point is that we're going to do some sort of induction to prove this. And the induction, right. So the induction is by, maybe I am actually going to have to figure out how to define logarithmico-exponential functions in terms of algebraical functions. Right, as the results are true of algebraical functions, it is sufficient to prove that if true of L functions of order n minus 1, they are true of L functions of order n. Right, so basically what is being said here is that, like, we are saying, yeah, we're doing like saying let n equal f dot order, induction n, generalizing f with 0, sorry. Okay, what's going on? Yeah, so I'm supposed to be able to get an explicit pattern match. Yeah, great, okay. So the point is that n is the order. Okay, but I probably also want the actual like assertion of equality. Let x t adds the definition x of type t is equal to e is there not a way that I'm able to say that like I also, okay, I have n is defined as f dot order, but what I want is like an hn, which says n is equal to f dot order as like a manipulable hypothesis. And I thought there was a way of doing that. Let x colon t colon equals e. Uses the type of e for, yeah, okay. Let colon t use this, yeah, pattern. Let eq colon equal h pattern e. Is it set? Maybe I need to do like set. Set with h. Yeah, okay. I think this is right. With hn. Okay. So now I'm generalizing f. Okay, so I think this is right. So now I have n is equal to f dot order. Yeah, great. And the point is, what Hardy is saying to do is you can do it by induction on n, right? So if n is of order 0, then we have an algebraical function. Right, the point is that f is essentially an algebraical function here. And so I will write a comment to that effect. F is an algebraical function. And then the hard part of the proof is proving the sort of inductive step. If it is true of all functions, yeah, just so this is the inductive hypothesis, and what we're trying to prove here, n f h n. Is that how I have to write it? Why am I? What's this n being hidden here? Yeah. Okay, is there some way that I set a as the hypothesis does not do any replacing? Yeah, okay. Right. Induction n generalizing f h n. Induction n with 0. So I have n. Okay, maybe the point is that it should be like n prime or something. Right. So I have n is the order of f. I might actually have to do strong induction. Let EQ, is that what that said? Let me go back to the let. Let, like the syntax let pattern, but this is not a pattern. This is just is the point that this is like a trivial pattern? Ugh. Equivalent to match, which adds the equation. Okay, so it adds an equation, but you're saying I can still do this? Like, okay, I'm just supposed to put EQ equals H. What is EQ? Like this, so EQ is like a keyword, is what we're saying, HN. And this puts that in the context. Yeah, okay, I guess it works exactly the same as the set way. Okay. So yeah, n is the order of f. Okay, so back to where I was. So this is a nice equivalent way of writing it. Okay. There exists a c greater than 0. Yeah. Okay, so the point is that now I have to like prove this theorem. Is true of L functions of order n-1. They're true of L functions of order n. Definitely need strong induction. Yeah, that's what I'm beginning to suspect. You'll definitely need strong induction because of the max parts in order. Although the order thing redundant because you can just induct on the structure itself. Yeah, well, that would definitely be my instinct. Is like, can I just induct on the structure of the can I induct on the structure of the structure itself, right? Induct on the inductive. But I'm also, I guess, a little nervous because the point is that we're going to be taking derivatives of L functions. Here, let me read a little bit more of this, right? So we already read this. We don't have to do the second part of the theorem. The derivative of an L function of order n is an L function of order n or less, right? So just to like double check, right? If I take the derivative of like the log of something, then that is like the derivative of the log of f is the derivative of f over f, I think. And the point is that both of those, like that, all I'm doing there is dividing, and so this is probably its own inductive proof, frankly. So maybe what I think what I may need to do here is define like a formal derivative on logarithmico-exponential functions, and then prove that it right. So like I can do deriv, right? Let me try that. Def logarithmico-exponential dot deriv. So just in the same way that I can like define a formal derivative on polynomials, I can define a formal derivative on logarithmical exponential functions, which takes a logarithmical exponential function to another logarithmical exponential function. It takes a constant to constant 0. It takes ID to constant 1. It takes the add to the derivative of this, right? We're doing like definition by induction here. It takes the mul to, I take the derivative of the individual parts. Negation, it takes the derivative of the negation of the derivative. Inverse, it takes right mul. So yeah, we're just doing some sort of weird okay. The derivative of 1 over f, as we recall from calculus class, is I think like it's like f prime over f, negative f prime over f squared, and that's what this is, negative f prime over f squared. Yeah. And then the derivative of the logarithm is the derivative of f over f, and the derivative of the exponential is the derivative of f times the exponential of f. Yeah. And so there's some theorem here about how derivative doesn't decrease the order. Yeah, so there's going to be like a lemma, like, so I have the derivative and I have the order, and I have to say that deriv does not increase order. And I can say something like lemma. This is a lemma. Dot deriv orderly, and this is probably okay. So what do we have here? Is this the correct statement? The derivative of the order of the derivative of f is at most the order of f. Yeah, and this is true. I'm just going to mark it as sorry for now. Okay, so we have that. Yeah, it's definitely going to be like a strong induction. Yeah. Generalizing. I can do both generalizing, like using, it's probably like using that dot strong induction. Maybe using has to go first. Using that dot strong induction on, generalizing those other things, alternative H's. Okay, but now I have to can I get the little light bulb? Yeah. Okay, so now I have to prove this. Wonderful. Okay, returning back to the paper proof. The derivative of an L function of order n is an L function of order n or less. Hence, it is enough to prove that if the results are stated are true of L functions of order n minus 1, then an L function of order n is ultimately continuous and of constant sign. Because if this is true of any L function of order n, it is true of the derivative of such a function, and therefore the function itself is ultimately continuous and monotonic, right? So the point is, we have the ultimate constant sign part and the ultimate continuous and monotonic part. Is the ultimate continuous part like easier to prove than the rest of these things? I think he might say at some point that the like that you could like, because I'm sort of interested in breaking this function up. I don't want to like have to prove all three of these things in simultaneity if I don't have to. So I'm just trying to think if there's a relatively simple proof of the fact that these functions are ultimately continuous. I guess the issue is that they're not necessarily ultimately continuous if we don't already know that they're not like oscillating up and down around 0, right? Because if they're oscillating up and down around 0, then it could be that the logarithm of such a function would be not eventually continuous. Okay, so it is sort of complicated. But the point is, it is continuous and cannot vanish for a series of values of x increasing beyond limit. In other words, it eventually is of constant sign. This is just a fancy way. This is part of what like makes me really frustrated. Is like previously he said like ultimately of constant sign, and here this is just another way of saying that. Okay, I guess he's saying it's like ultimately continuous and of constant sign. It's not clear to me like how this increases my understanding. Ultimately continuous and cannot vanish for a series of values of x increasing beyond limit. Right? Yeah. Okay, that's what it means to be ultimately of constant sign. For if this is true of any L function of order n, it is true of the derivative. Right. Okay, so like trying to think through this again. The point is, we're trying to prove that it's true. We're trying to prove that this whole theorem is true for things of order n. That is where we are at this stage in the proof. N prime, IH. We're trying to prove that this is true. We have that it's true for all lesser n. Wait, maybe have I stated this right? Yeah, the continuity should follow trivially from the sign part. Yeah, log and I guess also this inverse, which I've included. Right, the continuity should follow trivially from the sign part, because if I know that I am, I know that if I'm continuous, and I know that if I'm on constant sign, right? So like, if I'm a function, and I know that my derivative is continuous and of constant sign, that is really just like that. That is exactly what it means that I know that I'm monotonic, right? Or at least it's enough to prove that I'm monotonic. So basically, I've proved it already for all things of lesser order. And it's sort of like a sort of zigzag induction, right? The point is, like, if I draw it out, the point is like continuous and const sign for order 0 implies monotonic for order 0, because if I'm monotonic, if I know that all order 0s are continuous and constant sign, then for any order 0, I can take its derivative. I know that that is continuous and constant sign, and so I know that my function is monotonic. And then I think the next thing that we do is going to be saying that monotonic for order 0 should be enough to prove continuous and constant sign for order 1. Or at the very least, so basically the point is, I guess it's like, okay, what are we doing here? Can we boil this down into like an actual proof step? The point is that we're trying to say that this is the point, I think, is that we're doing like a sort of suffices step here, right? We're saying it suffices to prove that okay, let me like read again what I have here. Why is n not equal? Why is n prime different from n? What I wanted to be able to say was that I have f of order n, and I know that for all m less than n of that order, what I want is to clear the let, right? isn't there like, I don't actually want the definition of this to be here. I want to say something like clear. Is there like a clear let? It's like a clear n or clear depths. Ugh, I wish. Okay, this is why it's like there's got to be some sort of like all tactics, right? There's like this page of all tactics, and there's something to say like clear value. Yeah, this is it, I think. Clears the values a local definition, right? Yeah, so I think it's clear value. Right, like I'm saying n is the order of f, but I don't want anything else. Clear value n. And now unnecessary, okay, so that like changed things, right? Which is probably good because probably the generalizing. Hn is generalized automatically. Okay, great. And now what do I have? Yeah, okay, no. But I still have that n prime is the order. Okay, so now things are more unified, and I feel like more confident that I have the correct thing. Yeah. So yeah, so I think the basic structure of the proof is continuous and constant sign for order n implies monotonic for order n, and continuous and constant sign and monotonic for order all m less than n is enough to prove continuous and constant sign for order n. So I think that's the two theorems that we have here. Let me just like reread this to make sure that I'm not crazy. It is enough to prove that if the stated results are true of L functions of order n, then an L function of order n is ultimately continuous and of constant sign. For if this is true of any L function of order n, it is true of the derivative of any such function, and therefore the function itself is ultimately continuous and monotonic. Yeah, I basically just want to like factor this proof so that I don't have to write the whole proof. So let me just like try and write this as a lemma. The point is I'm writing a lemma called logarithmico-exponential function dot main lemma. The point is, let me like try and just like really capture exactly what he's saying. It is enough to prove that if it is true for all so if I have like an n, and if I say for all n prime less than n, it is the case that for all functions of order n, this should be hn, right? Yeah, this is okay. There's like it is enough to prove that if the stated results are true for L functions of order n minus 1, then an L function of order n is ultimately continuous of constant sign. So I have all the results for n minus 1. And I guess less, right? I feel like that's maybe not clear. I'm pretty sure that you do need them to be true, not just of L functions of order n minus 1, but all orders less than n. So the point is I have this lemma that says that for all n and all f of that order n, it has these properties. Then I can prove f of order n. We have just, so we have this, but we have just the Unexpected token. What? Oh, okay. Yeah. Sorry. Okay, but what I think I've duplicated here is essentially just the exact statement that we have here. Yeah. But the point is, I don't need to include the monotone antitone part. I don't need to include the monotone antitone part because I can prove that from the rest of this. So now what I'm going to do is I'm going to say like have main lemma, and I haven't done it right. I need an n prime, so I think it's n prime. Main lemma n. Do I have both? Yeah, it's n prime here. Okay, I've messed up like there's like a n prime. I can do a symmetry here to make it not bad. And I can also maybe write this in this way. It's telling me ruffle, but who knows? So this is, I also want hn. Okay, I'm getting close here, right? The point is I have, okay, so this gets me part of what I want. So this gets me like the first part of what I want. Like it occurs to me that like I should probably not be like phrasing these as exists c greater than 0. I should be saying like eventually. I should be doing like the for all. They're like, I don't know if there's like a more filter-centric way of writing these theorems. Okay, but so I think so. I've applied the lemma once, and I actually think I have to apply the main lemma again, right? So I apply the main lemma once to get the first part, and then I apply the main lemma again to add the derivative of f, right? So have logarithmico-exponential main lemma n to f dot deriv. Lemma for f, lemma for deriv, application type mismatch. The argument has order, but is expected to have type deriv order. Yeah, okay. Yeah, I see what the complaint is here. Right, the point is that I could say something like f of order is less than n, less than or equal to n. And now this would be a complaint, but this would be like by exact Ellie ruffle. Just put like by sorry there. Point is that this is not hard to prove. And the point is also that this is not hard to prove because this is a statement about the derivative order. Yeah, so the derivative order, this is like an application of the lemma that we had before. So now we have these two theorems, and we do some obtains, and we do some more obtains, and then we use let c equals use this. Yeah, great. And it's just gonna like do the rest of the proof for me, right? Like grind. Grind failed. Too bad. Okay, we don't actually have to like define something else here. Let me just use this max thing. And now the point is, it's just a bunch of manipulation. So I think that this is a sorry, right? Right, now would be a good time to break out the AI, right? the trick, okay, the trick is that I'm here in MathLive. I should see if I can like install this in a different repository, because I don't currently have the Numina LSP MCP installed here, but that would like definitely make it easier to like complete a bunch of these stories by AI. Let me like see if I can do that. I was working at like CS Lab, so this is going to be a little ridiculous, but maybe it's not ridiculous at all. In fact, like this is a entirely appropriate thing for CS Lab, right? So I can put this here, and I can do, okay, so this is going to be my like orders file, .lean. So I'm going to copy all of this, and now I'm working in this, but I think I have like all of these like Claude tools that I have installed. Okay, so like what happened? So can I successfully do this? Let's try AI theorem proving. Please go through the files or the saris in this file and attempt to prove them. Okay, so this is like a nice step that will hopefully catch if I've like made any like major errors. And okay, so it's not going to be able to prove all of the saris, because then it would be like skipping all of the like reasoning here. Presumably it would, I'm probably gonna have to tell it about like the rest of the reasoning in the section in order for it to be able to complete the proof. But it should at least be able to do some of these saris. Like it's gonna do this. Yes, allow all edits this session. Okay, so these are probably like various grind things. Derive order LE. Exact max LE max. Yeah, I think the inverse doesn't cause, so it's confused about the inverse, but let me just like check. This doesn't cause any problems because neg doesn't increase order, mul doesn't increase order, and we have derive, which is the only thing we needed anyway. Okay, yeah, wonderful. It was successful in proving this theorem. Okay, so now it's going to move on to some other theorems. The main lemma, it's going to fail. I was like, skip the main lemma. Can I just do it while it's working? Yeah, because this is the one that it's not going to be able to prove, because this is the one that requires the reasoning of the whole rest of the section. But this, it should be able to prove because it already has access to the previous lemmas. And the point is that this is just like some simple combination. And it should actually also be able to do all of these because these just follow directly from the main theorem. Okay, great. So while it's thinking about that, I'm going to return to thinking about the main lemma, right? Which is that it is enough to prove that if the stated results are true for L functions of order up to n, but not equal to n, then an L function of order n is ultimately continuous and of constant sign. Or if this is true of any L function of order n, it is true of the derivative of such function and so ultimately. Okay. Now, okay, here we get into the part that was sort of very confusing me, but let me do my best. Any L function of order n can be expressed in the form of such, where a denotes an algebraical function. So yeah, like, so in my terminology, I guess, like, think of this as like a rational function. And the point is that we have to like remember all of the like notation that has been defined. He's defined like E as like exponent and L as logarithm. So it's just like but the point is that f of n is an algebraical function of a bunch of n-1 order functions raised to e raised to the power of a bunch of order n-1 functions. So, okay, so the subscript, yeah, this is very confusing to me because I'm used to subscripts denoting indices, but that is not what they're denoting here. They're denoting just like the order, right? So we have a bunch of functions of order n-1 that we have exponentiated. We have a bunch of other L functions of order n-1 which we have logarithmed. And I guess we have a bunch of other L functions which are of order n minus 1. Why aren't these functions of order n? I guess the point is that if these were functions of order n, we could decompose them further, right? If these were functions of order n that were not exponentiated or logged, we could decompose them further until they were exponentiated and logged, right? So the point is, okay, we are going to look at your structure, we are going to decompose the structure and stop at the point where we reach an exponential or log, and that will give us some algebraic function structure description of f, right? The subscripts are always the orders, but it's just going to give us some description. And so the point is we have some big rational function of all of these things, and I think it does have to be a rational function, because I was wondering if it could just be like a polynomial, but I don't think that that necessarily works. So we have this algebraical function of all of these different parts, and they're all n minus 1 L functions. See, the next part that confuses me is this: like, why would there be any functions? Why would there be any unexponentiated or unlogarithmed functions, right? I feel like I could just say, forget about these chi's, right? F of n is going to be of the form of an algebraical function of a bunch of exponentiated order n minus 1 functions and a bunch of logarithmed order n minus 1 functions, right? Because I just am decomposing until I get to the exponents and the logs. Okay, whatever. The superscripts denote the indices. So Q is r plus s plus t. The functions with suffix n minus 1 are L functions of order n minus 1. And A denotes an algebraical function. Okay, so can we write this as a theorem is the question, right? What I want to be able to say is that, like, using the terminology that I have here, where I have this algebraical function, like, I want to say, like, if I have an algebraical function, right, again, I'm running into the issue that I want to be able to express multiple arity, like higher arity for the algebraical functions. But if I did include like a arity algebraical function, then I could say, like, for any logarithmico-exponential function of order n, I can say that there's an algebraical function of logarithmico-exponential functions such that it's the composition and that all of the composed logarithmico-exponentials are of a smaller order. Okay, what is this? It's asking me about a bash command? No, no bash command. Do this without bash commands. Okay, what has it done? Has it, like, main lemma is the core inductive lemma. Fill the simpler saris in main theorem. Yeah, okay, so it just got hung up on something and it didn't do any work while I was thinking about that other thing, but now it's thinking again. Okay, yeah, so it's successfully doing these, like, lemmas based on this. Great. Okay, so yes, back to this. A denotes an algebraical function, and we have an algebraical function of logarithmico-exponential functions of order n minus 1. L functions. I should just say L functions like he does because it's logarithmico-exponential. Okay. The coefficients are polynomials in Z1 through ZQ. Okay. Yeah, no, sorry. I need to think about this again. Right. I got confused a long time by this statement. And I think okay, yeah. So, A denotes an algebraical function, and there is therefore an identical relation f, big F, no definition of what big F is. Like, what is big F? Why even write big F? I'm pretty sure that, like, big F doesn't come up again, so why write a symbol for it? So there is a relation m0 fn to the p, m1 fn to the p, where the coefficients are polynomials in z1, zq. And the point is that this is an identical relation to n f of n being this expression, right? So if f of n is this expression, then f of n. So I think that the key part that was confusing me for a long time about this is that this weird relation thing has a lot to do with the roots, right? The point is that, okay, if it's an algebraical function, there could actually be roots in here. And so because there's roots in here, I might at some point need to say, for example, if f of n was like square root e to the x, then what I would want to say would be that f of n squared f of n squared minus e to the x equals 0, right? And the point is that I would need an exponent. I would need I would need an exponent here, because to square everything I would need to exponent. But if I am not having the if I'm not having the roots, I don't necessarily know that I need to do this. So I think I can maybe simplify this statement to just there is a relation like f of n is equal to some polynomial. Basically, the point is that f of n is just some rational function, right? Which is tantamount to all that I've already said, because I've already said that I'm basically treating algebraical functions as rational functions. So this line really confused me for a long time, but I think the point is I can just if I do this manipulation at the beginning, which for whatever reason Hardy didn't do, of defining the root in terms of the other operations, then I don't actually need to think about this line, and I can just proceed to the next line, which is to say that the f of n is a rational function, right? Or maybe I have to say that it's a polynomial, right? I might have to say that I might have to okay, I have polynomials of p, but maybe I can make it a 1-degree polynomial. It's tricky because the z's coefficients are the polynomials in z1 through zq. Yeah. Right. Yeah, the coefficients are polynomials in this. Great. But okay, so what is the equivalent thing that I'm trying to say? The point is that if f of n is an order n L function, then it can be written as a fraction of two polynomials if I think what this is trying to say is the following. If f of n is an L function of order n, then it can be expressed as a fraction of two polynomials in the class of the following functions, right? Where basically I have, and so this is the part where it just continues to get more and more confusing. We've removed, we only have one e here, because if we had multiple e's, we could just combine them, right? Because a product of two exponents is an exponent of the addition. Okay. Okay, so Claude is done with its work. So it didn't prove the main lemma like I told it not to. And the only thing left is, okay, so I didn't successfully prove this. What went on here? So I decomposed this, I was able to successfully prove these two parts. And then the point is the monotonicity should follow from the derivative part. Right. The point is that the derivative is of constant sign. So what I'm going to say is prove the highlighted sorry by casing on whether the deriv is constantly 0, is, I guess I should say eventually 0, positive, or negative sign. And maybe the issue is that it needs to prove a lemma about this. You may create, I'm going to say, you may create new lemmas if you need to. Tell it to do that. All right, so while that's thinking about that, I'm going to continue thinking about this. So it's a rational function. F of n is a rational function of a bunch of I think it's just a rational function of a bunch of exponents and logs of order n-1 L functions. Maybe the terminological issue is that in Hardy's definition, the order is not just an explicit number, it's actually just like a bound on the number, right? So I think that the way Hardy is defining things, all order 2 L functions are also order 1 L functions. It's like the order it's not like it has a fixed order, it's more like a relation between L functions and naturals. Downwards closed relation or whatever. Okay, but the point is okay, let me try and summarize all of this. I think what this is trying to say is that if F, I've repeated this several times at this point, becoming more and more elaborate, but let me try and do it one more time. If f of n is an L function of order n, then it can be expressed as a fraction of functions of this form, where these are all the subscripts denote order n-1 or less L functions. And the kappas, I guess, are positive integers, I guess, because we're working with polynomials. The number of terms in the summation is finite. Yeah, okay, great. And the functions with suffix are again L functions of order n-1. So also are the derivatives of the m's. And the discriminant of f qua function of f. Yeah, so. Right. I don't think we have to worry too much about the discriminant. Because what I'm trying to do is I'm trying to say, okay, there's a simplified form of this proof where it's just a rational function. Let us suppose our conclusions established so far as relates to functions of the type m. Yeah. So basically, we're going to work our way up, right? So in fact, there's actually an even subtler form. There's actually an even subtler form of complexity, I think, which we're about to get to, which is the degree, right? Which is the degree of this, right? Let us, where was I? Let us suppose our conclusions are established so far as relates to functions of type n. So he's going to say something like, okay, it suffices to prove that the functions of this type have the properties we need, because then it will be possible to just it'll be possible to prove that they're the division of one by another. It follows by a well-known theorem, which he has in terms of this here, but let me see if I can reason through this, right? Let us suppose our conclusions were established so far as relates to function of the type m. Then it follows by a well-known theorem that the division of those two functions, f of n, is continuous, right? So if I have m0 and m1, and I know m0 and m1 are both eventually continuous, then I know m0 over m1 is eventually continuous. Yeah, I buy that. And since f of n equals 0 involves mp equals 0, then f of n is also ultimately of constant sign. Yeah, so I think I've successfully avoided this well-known theorem, and I'm just saying, okay, if I divide two functions that are both ultimately continuous and ultimately of constant sign, I get a function which is ultimately continuous and ultimately of constant sign, because, right, is ultimately going to be continuous because the divisions are ultimately continuous. Okay, well, no, I need to think a bit more carefully, but I still think I'm right, right? It's ultimately of constant sign, right? I have that both m0 and m1 are ultimately of constant sign. So if they're both ultimately positive, and they're both continuous and ultimately positive, and so their fraction is continuous and ultimately positive. If one is positive and one is ultimately negative, then they're continuous again, ultimately positive, and ultimately negative, right? If one of them is ultimately 0, then because luckily, I think I'm sort of like maybe experiencing fortune here, right? Luckily, because of the conventions, right? If either one of them is ultimately 0, then the fraction in the junk value formulation is going to be ultimately 0. And so that will again ultimately be continuous and of constant sign, namely 0. So I think that this is fine. Okay. I'm wanting to start writing here. Did it succeed? Okay. So it said derivative is 0, but did you make more lemmas? Right, okay. The syntactic derivative, you made more lemmas. Like, okay, but I want to tell it, like, prove those lemmas. Because I want to make sure that you, you didn't misformalize anything. Is this true? The syntactic derivative agrees with the calculus derivative. Yeah, that's sort of what I want to say, right? If it's continuous. I don't know if these lemmas are actually true or not, but hopefully there's not too much of an issue with them. Yeah, okay, whatever. It is enough to establish our conclusions for functions of the type M. Right, okay. I feel like what I want to do now is I want to like state the theorem about like what I'm trying to claim about L functions of order n, right? I want to state that the L functions of order n can be expressed in this form. And it's tricky a little bit because there's a big operator here. Right, we've already established everything we need to know about the n-1s, and we just need to do the order n. Oh my god. Look at all these unsolved goals. Okay. I'm going to tell it to like stop here and go back to sorry form because this is too much. Okay. And I want to like say other things, and I don't want it to like be writing over what I'm saying. Okay. So the point is we have all of these. We have this main theorem in terms of some other things. And we want to proceed with the main proof. So this is the main proof that we're doing. The point that we have is that lemma, logarithmico-exponential. Okay, this is the the namespacing is getting a little boring, so I will try and make a namespace. Logarithmico-exponential. What am I trying to say? The point is, like, is div of order. And so the point is, I have f is a logarithmico-exponential function, an n, and like I could say something like this. Yeah, probably. I want to say that this is of a certain form. Yeah. Because I'm going to need to start passing like lists or vectors or something, because this is going to be yeah, I'm gonna need to start passing lists or vectors, because I want to be able to express the notion of it is a polynomial over many other things. Let me just go back here, right? The point is that this is a polynomial, right? This is just a sum of a bunch of things. Finite number. Yeah, so I'm going to want to say something like, I'm thinking if I like need to just like define a bunch of other additional types up here, inductive types up here, to capture what I'm going after. Like I want to define like different particular classes, right? So like I could call this like the class of like terms, right? The class of m sum terms, right? Like in inductive m, it wouldn't even be like a struct, it would be like a inductive m sum term would be a like, so wouldn't even necessarily be that. It's just a regular form, right? And it would be like a row, which would be a logarithmic-exponential function. Okay, I need to clearly do this here. It would have a row term. It would have I guess I will call this a sigma term. And then it will have a bunch of tau terms. And this is actually going to be a list. Now, okay, these are positive integers. So I think I don't actually have to say they're positive integers. I can just have a list with duplicates. So I'm going to say that this is like a list. So this is the m term sum. And this is like probably a dumb way of doing it, but I could also say like a structure sum equals a list of m sum terms. It's just a def. Yeah. So I have these things, and I have ways of interpreting these as logarithmico-exponential functions. And the point is that every one of those, yeah, so there should be like a def m sum term dot to logarithmico-exponential. And I also want to be able to do this for m sum. There is an interesting wrinkle here, though, because they're rational functions. Yeah, the wrinkle is, here's what I'm afraid of, right? I have these things and I'm computing the logarithmico-exponential, but I'm worried that, like, I can't say that, like, the logarithmico-exponential that I have is equal to one of these terms, because really what is equal is just their evaluations, or maybe even their evaluations aren't equal because of like weird junk value things. They're just like what I know I can say is that, like, for every, the point is that I have the following theorem. Let me try and write the following theorem. I've defined the order. This is the theorem that I wanted. The theorem that I wanted is what? Well-formed at. No, I don't necessarily want this. I mean, like, maybe. Maybe, okay, so maybe this is like invention of the okay, but here's, yeah, so this is where I was. The point is I actually want to say the following thing. There exists m0 and m1, which are m sums such that f equals div. Okay, but this is not true. Sorry. This is what I want to write, but this is not true because, like, these are saying that they're equal as, like, expressions, and that's not what I want to say. I want to say that they're equal as not as expressions, but as like functions. So what I sort of want to say instead is like f dot eval is equal to this. And this is the lemma that I'm sort of interested in. Okay. I'm not entirely true. Like, note to self to do. Is this true, or is it only true on all but finitely many points? That is the question. Okay, but the point is that I think that this is true. Like, something like this is true. F is frankly like a division of two things of this form. I may have, yeah, I think it's a division of two things of this form. It's not exactly what's written here because there's just like a missing negative sign or whatever, but F is a division of two things of this form. And the point is, like, the point that we're going to proceed to do now is, like, okay, we have our lemma, right? Our main lemma is something like this. And the point is that, okay, we're going to do like a main m-sum lemma, which is doing this, but not for logarithmico-exponentials, but just for m-sums. And to prove the m-sum lemma, we'll do it for m-sum terms. Main lemma m-sum. This is going to be an m-sum, I think. Dot to logarithmico-exponential. So I think that this is what I'm going to prove first, right? I'm going to say that f is sort of like this. Then that means that it's true here. And then that further means that it's true for m-sum terms as well. So m-sum term. And it's like I have to do one after the other, right? The fact that it's true for m-sum terms means that it's true for m-sums. Well, okay. At least the fact that it's true for m-sums should mean that it's true for main lemma, because the point is I can rewrite f as a division of m-sum terms, and, you know, everything follows. The fact that it's true for m-sums should follow from the fact that it's true from m-sum terms. Is that true? For functions of the type m, maybe I don't establish it for m-sum terms, because this is like a sum. It is enough to establish our conclusions. Let us call the degree of a term of m. Yeah, okay. So this is just the number, right? It's just the length, right? The degree of a term of m is length. And let us suppose that the greatest degree of m is lambda. And there are mu terms of degree lambda. And that the term printed at, yes, so this is like all of the things that we're going to prove that we're eventually reducing. And that the term is printed in the expression of m above is one of them. The first place, it is obvious from the form of m and the fact that ey and ly, exponential of y and logarithm of y, are ultimately continuous when y is ultimately continuous and monotonic. Yeah. It is obvious that it is ultimately continuous. Okay, so yeah, what's being said here is that I can actually break this up further. Okay, I think I should not have written this. I think I should not have written this lemma. The point is that this lemma implies this. Use m-sum. So this uses this lemma, and this lemma uses... The point is that I'm now going to like further break this up into part 1 and part 2. Part 1. This is part 2. And this is, I have this something. Continuous on. So the point is that part 1, like the continuous on part is relatively obvious, I think. And this is... Right, this, like, what is that? This follows from the fact that everything else is eventually positive. The first place, it is obvious. Okay, is it obvious? From the form of m, that the fact that are ultimately continuous when y is ultimately continuous and monotonic. Yes, so we already know that the things in here are continuous and ultimately monotonic. So we don't have to worry about like, oscillating around 0 here. And therefore, m is ultimately continuous. So we can get that m is ultimately continuous. Again, if m vanishes for all values of x surpassing all limit, for values, okay, putting it in not archaic language again, if m were not ultimately of constant sign, if it oscillated up and down around 0, then The same would be true of this. And therefore, by Rolle's theorem of the derivative, yeah, so the point is now that we're going to do a two-part induction, first on the degree and second on mu, the number of terms of that degree, right? The point is that we're always reducing the number of terms of the maximum degree until we get to 0 terms of that degree, at which point we have a smaller degree. And so we're going to smaller and smaller degrees. The reader will easily verify that when we differentiate and arrange the terms of the derivative in the same manner as those of m, we obtain a function of the same form as m, but containing most mu minus 1 terms of order lambda. Repeating the process, we ultimately arrive at this form, where there are no factors of logarithmic form, and it must vanish, right? Like the point is that this is, right, like we already know this vanishes. We already know that this doesn't vanish, and e is just a positive value, so that's fine. Okay, maybe, yeah, I don't know. Yeah, I feel confident that like now that we've gotten past like this hurdle, the part is just doing a bunch of like tricky inductions on these to prove that this is true. So that maybe this is a good place to stop or take a break at least, just because, okay, like probably the next is going to be like a slog with a lot of details, and it'll be good to be well rested for that. So I think I'll stop it here.